Hello, my name is Niklas Kleve. Today I'll talk about automated measurements of castings during series production. Right here you can see our scan box 4105. This is our smallest scan box out of 6 different types. They all have a similar structure, and normally you can transfer the measurement programs from one scan box to another. Our customers use our scan box mainly for 3 applications. Firstly, before starting production as such, the stage where the product is tried out. Here the non-contact measuring system is more convenient than tactile probes because there's no probe that could break off. And the measuring object and the sensor are so far away from each other that there are no collisions. So, as there is no contact during measurement, neither the object nor the sensor can be damaged, and we still have the option to change dimensions and the geometry. The next step is the production phase, where everything is up and running. The sensor always scans the parts at the same positions, one after another, as they come in. The third step is measuring without gauges. This means we can measure parts without any fixtures at all, or with fixtures that work for multiple parts. You need less storage bins, and you can minimize manufacturing, maintenance and servicing costs for gauges. All of those costs are gone. Before I turn to the kiosk, our user interface, to demonstrate the scan box, let me talk about the part's history. Even though most of you probably know it already, I'll give you a brief overview. Right here you can see the tool we use for the wax pattern. The wax is injected and the pattern is produced in the middle. That's it in brown. That's what it looks like in the end. The wax pattern is then mounted onto this tree and dipped into a liquid which creates a ceramic coating. The pattern is immersed several times to create a ceramic shell. We then heat up the tree to cure the mold. The wax melts out of the mold, and then you can start to cast the part. We then pour material into the mold to produce the part, and after cooling, the parts are removed from this tree. After completion of this process, you can demold the part and put it into the scan box. Let me just do that. I'll enable the scan box, and now the sensor can start to scan the part. First, however, I'll have to open the kiosk mode. Ready. I'll use this barcode scanner to scan a code. This code is a unique part of the serial number and opens the template in the software. This means our kiosk mode now loads the template which corresponds to this barcode and its numerical code. Now I can verify whether this virtual setup resembles the real setup. Are there any potential collisions or similar risks? If I'm happy with the setup, I can initiate the measuring process. The scan box is measuring the part, and in the meantime, I can explain the sensor and the scan box to you. That's our ATAS capsule, our sensor for small and medium-sized parts. It has an encapsulated housing, as you can tell from its name. It protects the scanner from splashing water, dirt and other contaminations, and it also features a self-monitoring system. The scan box has a calibration plate, which is mounted back there. And it has reference points on the rotation plate, as well as on the fixtures, which ensure that the system permanently monitors itself with its 2 lenses. It knows whether it is still calibrated or not. It can also detect vibrations, etc. So it is completely self-monitored. As mentioned, we've got 2 lenses and in the middle a projection unit. This unit projects a pattern onto the part which we can see right here in blue. The system uses it to generate the 3D data which we evaluate with the software. Normally the scan box has 1 axis serving as rotation table and the robot has 6 additional axes. So altogether we've got a 7-axis system allowing for a high degree of flexibility where we can measure many areas. Let me turn to the triple scan function. This sensor can use either the left or right camera, or both simultaneously, each combined with the projector. This means we have 3 configurations. The scan box, as you see it right here, can measure parts up to a diameter or height of 500 millimeters and parts with a weight of up to 100 kilograms. Of course, larger scan boxes can measure even heavier parts. It also has casters, so you can move it around on the shop floor or wherever you want to, so the scan box is not stationary. Now let's talk about safety. The scan box has an emergency push button in front and on the touch panel, so you can stop the system anytime. But safety starts as early as in the software. The software will inform us about potential virtual collisions and other risks. And in such cases, the real system won't even start. You can imagine that these features are very efficient. We also have an integrated torque limiter. If the torque is too high, everything also comes to a halt. Okay, so much for the software. The scan box finished measuring the part. The project is being recalculated, and now the operator can browse the report pages to decide whether the part looks the way it should. So let's have a look at the results. Right here, for instance, I can see the alignment. But especially for this part, we can use a specific evaluation package for airfoils, which I'll explain on the next slides. Here you can see the surface comparison, which is the deviation between actual and nominal values. Here you can see the sections at defined heights. We can now inspect these sections by using what we call the airfoil or turbine blade evaluation. Here we've got a specific functionality with all kinds of functions. For instance, we can analyze the leading or trailing edge, whether the circles are positioned in the right area. In the middle, we see the camber line, which you can also analyze. All of these features are part of the airfoil package. I'll explain it briefly. You can also convert everything into a table. Here you see the lines you need, angle analyses, everything included. You can also determine the output angle and list it in a table. The shape analysis is another feature, with profile twists and other shapes. And deviations are shown, for instance, in a color plot, as you can see right here. Once you've run all of those evaluations, and provided you're satisfied with the result, here we have a nice final table, you can either accept or discard this result. I'll say I'll accept it, and the system automatically generates reports. The PDF is saved, and the project is saved as well. Now let's turn to the next item. Let's say we've scanned 10 of these parts, and now we'd like to know, is there a specific trend? What does the trend look like for the parts that I measured? This is where the trend package comes in, which allows us to analyze these stages, as we call them, for a defined number of parts. Here, for instance, in gray, we see the measured data. We can browse this trend project and we'll see that as the alignment changes, the real data also change compared to the CAD. This is reflected in the table. And now let's have a look at the report and its different plotting and visualization options. Here we can see the trend in a graphical plot. And you can see straight away that we've got an outlier right here. And that's still the standard trend table. You can also see the results as deviation per stage by applying the process capability indexes, that is, the PP and PPK values. And you can see the standard deviations, the range, minimum and maximum deviations. The third table we've got is the statistical RPS table. It shows you the deviations throughout all 10 stages. And of course, it also shows you the tolerance range, so it's really a nice overview. Right here, we can also generate exports. For instance, we can export all the tabular values right here as QDAS or PyWeb files. It's all there for you. You can also write your own exports. Our package includes the standard export formats that are typically used in many other packages. So much for the trend module. But actually you can also start your evaluation even earlier in the process. Right here we are measuring the finished casting. But let's say the mold is defective or the resulting wax pattern has to be optimized. Let me demonstrate this with 2 more projects. I'll start off with a comparison between actual and nominal, that is, between the scanned mold and the target mold. The 2 halves are aligned. We inspect them by using the surface comparison and deviation labels, and then we're able to inspect the mold along the inside surface where the wax pattern sits. Here the analysis shows me whether the tool has to be corrected or whether there is another mistake somewhere along the process. This is the first option. The second option is the complete virtual assembly of scanned data without CAD. This means I measure the tool in a closed state. I transform the halves to each other by using reference points, and then I can transform this wax pattern into data by using the best fit process. And again, I can use a surface comparison or section to visualize how I have to optimize my process. Do we have to hold the clamping pressure longer? Do we have to keep the tool closed a bit longer? Or do we have to change the material properties? Does the wax shrink too much during curing, cooling, or whatever? Here I can see the distance between an actual scanned part and an actual mold. This means I can make changes while creating my part. So much for the topics I wanted to explain. Let me wrap up. You've seen the fully automated use of the scan box during ongoing production. You saw how trend projects work, the available export formats. You also saw that some processes can be optimized at an earlier stage and not at the end of the process when the part is finished. Thank you for your attention and goodbye.